All right. So, good afternoon, everyone. I just want to begin by thanking you all for showing up. It means a lot for you guys to come out here for us to show you our presentation. My name is Sabat. I'm a member of Poseidon. Our sponsors are Mechatronics and Altium. And over the course of the semester, we've been designing, developing, and testing an acoustic modem that will be used for underwater communication. So, for a little background, our sponsor, Mechatronics, placed first in last year's annual AUVSI's RoboSub competition, and they were able to achieve this by getting the fastest time. And by getting the fastest time, they get a time bonus, and in a sense, to redouble their efforts and defend their title as last year's champions, they've innovated a new way for one RoboSub to actually act as two subs that would be working in tandem with each other to complete this obstacle course at a much faster time. However, the introduction of this new sub introduced a new problem, and that was a communication system that could be implemented between them. And to do so, we've tackled this over the course of the semester, and this video right here behind us kind of illustrates our achievements thus far. And to talk a little bit more about the course criteria and the competition, I'm going to hand it off to Jeffrey.
All right, thank you, Sabat. So one big thing to consider when designing a communication system is the environment for it to be used in. The big arena for underwater communications right now is, oil and gas and marine research, which is deep water and long distance. But our application requires a shallow water and short distance communication system, and that poses a different set of problems that we had to tackle this semester. And to kind of move on to what the actual application is, I'm going to give a really brief overview of what the competition is. It's basically an autonomous submarine in a giant pool, as you can see up here, and there's a bunch of obstacles set up that it has to go through. This is the first obstacle. This is just it going through a gate. The next obstacle is it going up and hitting a buoy, as you can see there. Just wait a sec to see that happen. All right. And then the final one that I'm going to show you is last semester we actually had a senior design project for this, where they have an active pinger under a PVC octagon. And what this submarine has to do is it has to find the signal, go towards it, and rise up in the octagon as you see it going towards right now. All right. Now to move on, Brady is going to explain our system and how we challenge this problem.
We're going to go over onto the software side of things. Today will introduce us.
Okay. So first I'd like to start to tell you about our goal. Our standalone goal for the semester for the software team was to be able to communicate between two PCs through the SPIC microcontroller. As for the semester goal, we like to combine our design with the hardware team, which enables underwater communication. And the final goal is to be able to integrate our design into Mechatronics' mother and daughter submarines for the 2017 AUVSI competition. And why do we do this? What's the big picture here? It's that we like to improve on autonomous robotics as well as naval construction and naval and ocean research. The language we picked for our software is Python version 2.7. The reason we picked this language is because it's compact. There is no compiling requirement. There is no memory management. It's the language that Mechatronics is using for their GUI. And the GUI library that we used is tk-enter. It also supports Python, and it's very well documented, so we had a lot of examples to go through. And the plotting library that we used is matplotlib, which also supports Python. It's made to resemble MATLAB, but it's open source, so the user doesn't have to pay for it. So we have two sources that generate data. One is the IUS, which is the Interactive Underwater Simulator, and the other one is the GUI, which is the Graphical User Interface. The IUS generates data in two different methods. One is the autoplay, which is just the submarine that runs off a script and generates the data. The other one is the user play. After the user interacts with the simulator, it generates that data. And the other one is the GUI. It also has a user input data, and the other one is the script. All this data goes to a digital board 1, which consists of a DSPIC33 microcontroller and an FTDI.
I'm not sure what you said.
I said that. So that FTDI board, which enables communication with PC. This data is received on digital board too, and then there are two ways that we display this data. One is in the GUI, and the other one is the live plotting. So as the data is being received, it's getting plotted. I'm going to pass it on to Blair to tell you more about our simulator.
All right, so as part of our product, we decided to create a simulation for it to visually display what our finished product should be doing. And so as part of this, we have two different game modes. We have just a regular play mode and an auto mode. And then instead of doing like obstacles like the actual sub would do, we're just having it collect coins just for simplicity. And it's just easy for the people to pick up and do. And so after you click one of these modes, the user is just seeing an objective screen, which just simply shows like just a brief objective of what they're supposed to be doing and acclimates them to the user interface quickly. And then next, they'll be shown like a user interface screen, which just shows them the controls for the game and points out all the different items on the screen for them. So in the first mode, it's just a simple play mode, and the user can control the submarine, go around, collect the coins, and complete the objective. They can also pause the game, restart the game, and exit to the main menu. In the auto mode, it just simply picks a random coin and goes toward that coin. And then you can just watch it play, and when you're done, you can just exit the simulation. So the whole point of the simulation is just to generate data. And so that data is generated every second by the game and is output to a file. And then we can use this file to test our system to make sure that it's working properly and to use in our GUI so that the way we know that is also working properly. And so I'm going to pass it off to Jonah to talk about the GUI.
So the GUI is graphical user interface, and what it's used for is to gather large statistics over a short period of time. It's also used by, it will be integrated into the mechatronics team, so we decided to create 4 tabs and 2 buttons. One is the launch game, one is the help tab, and for the welcome tab, it just gives you an overview of what the GUI is. The configuration tab shows if the FTDI board is connected through the USB into the computer, and the help will give you instructions on how to operate the send side. So for the send side, we have 3 data types. So one is input type. You can choose decimal, binary, or hex. For error correction schemes, we have Hamming or Golay. For data input, as Shade said, we could either the user manually inputs scripting, which generates random data, or the game mode, where it obtains the data from the game, the simulation itself. And the send button takes all those 3 into consideration and encodes the data accordingly. And to talk more about that is Trevor.
All right, so I'm going to talk a little about the GUI functionality. So as you see in your left-hand side, you see a user inputting the data in decimal, and then you will see it get encoded in the Hamming code selected, and blue, red, green, or purple. These are the 24 sub-packets that will be interleaved into the bottom text box in the colors corresponding. And then on the right, you see your receive tab. The receive tab receives it interleaved in the color codes on the bottom, and then we'll de-interleave it into the 24-bit sub-packets, and then decode it into the decimal value corresponding. And so now we're going to look at the game mode. So the game mode is playing on the left side and on the transmit side, and the right side is the graphs displayed on the receive side. So as you see, as the game is being played, the graphs are corresponding to what is happening in the game. So you see a depth versus time graph, you see a task counter, you see a distance versus time graph, and you see a heading graph. And so now, I'm going to talk a little more about the error correction schemes that we chose. We ended up going with Golay and Hamming. They are very robust schemes and allow for error corrections in these burst environments that we are expecting within the pool. They require 100% overhead, and to also further tackle the burst errors within the pool, we want to introduce interleaving. Interleaving basically will allow us to spread out the errors across different messages so it is easy to correct, as seen in the example. And then now I want to talk a little about the actual packets. So for the packets, there's actually 48 bits of data that will be encoded, and because of the 100% overhead, there will be 96 bits of data within the packets. Within these packets, there will be a frame ID, there will be a confidence, distance, heading, depth, and a task. And then now to talk a little more about the system communication is Captain.
All right, so the communication process starts at the microcontroller on the send side. We send a request to send signal to the PC. which means that the microcontroller is ready to receive the packet. We also send this signal to keep everything in sync, and it allows the modulator on the DS PIC to run without interruption. Once the PC receives this signal, the packet is fetched from either the GUI or the game, and is sent back down to the microcontroller and stored in a memory buffer. This is where the hardware team comes in and sends the packet across the water using FSK. They reconstruct the packet on the other side and send the packet up to the PC, and that's where we perform our error correcting algorithms and decode the message, and it will be displayed in the GUI. I'm going to pass it to the hardware team.
Thank you, Kevin. And with that, that wraps up the majority of our software side of this project. And entering the hardware side of the project, we immediately threw away the concept of this being a project and divided it equally into 3 parts or 3 teams that we felt would be able to tackle these issues. And these teams included the transducers team, an analog team, and a digital team. And to start off by giving you an overview of the hardware side, I'm going to give it to Brady to talk about the block diagram.
Thank you very much, Sabat. So I'm going to quickly go over the block diagram. As you can see on the left-hand side of your screen is the transmitting side. You will see two-way communication between the microcontroller and the PC, as Kevin elaborated on earlier. We will use SPI, generated by the microcontroller, to communicate with the modulator. The modulator will then generate the frequency communicated by the SPI bus. Then the power amplifier will amplify the signal, driving the transmitting transducer, sending a signal across the water. The receiving transducer will receive the signal, induce an electrical signal that will be processed by the bandpass filter, variable gain amplifier, and envelope detector to be read by the ADC channels. We also considered at the beginning of the project using a DSP filter. Next, I'm going to talk about the modulation scheme. There was 3 different modulation schemes that we first wanted to choose from. ASK, which is amplitude shift keying. This is based off of making a threshold. If it's above a threshold, it's a 1-bit. If it's below a threshold, it's a 0-bit. And on-off frequency shift keying. This has to do if there's a frequency present, it's a 1-bit. No frequency present, it's a 0-bit. And finally, frequency shift keying, which is a high frequency present is a 1-bit. A low frequency is present, it's a 0-bit. We chose frequency shift keying because it's the most robust and is immune to multipath. You can view multipath on the left side of your screen. As you can tell, reverberations across the pool cause a lot of problems when we're receiving signals. Amplitude shift keying causes problems with that because of the fact that we were afraid of getting reverberations, and we would see that later on because of the reverberations off of the walls and the surface. Next, I'm going to pass it on to Bao to talk about the microcontrollers.
Thank you, Brady. For microcontroller, we use PIC33. The reason why we use it because it has multiple channel of IDC and allow for parallel reading of envelope detector, and its stronger processing power, DSP, enable to solution to be implemented. And the last reason is the mechatronic they use PIC through the RoboSub and enable to accept the code written by them. And right now, I will pass on to Jiro for the DSP.
Thank you, Ron. So we didn't implement the DSP, but we thought it would be a good solution since our DMOD requires a few PCBs at the moment, including the envelope detector and the filter at the front. So the DSP is actually just a finite impulse response filter where it just burns up clock cycles to evaluate the filter at a specific frequency because our modulation scheme was FSK. So the memory footprint was less than 32 words. The execution speed was 80 cycles, which would take too long and we couldn't meet the data rate we wanted. Window size I picked was 392 samples. It could be changed with the coefficients. And to improve your SNR, you would oversample, but as you can see here, these are the highest frequencies we could detect. And for the next slide, this is an example of the DSP working. Over here on the first one, you can see it's detecting a high frequency, and you can see it's XXX for the first 3 because it's not on the center frequency. And then over here in the middle, it detects it at 98 kilohertz. And it's also the same thing for the other side, just detecting a low frequency. So you can see the filter has a sharp roll-off, and the magnitude is listed over there. And next, I'll pass it to Jeffrey for the digital synthesis.
All right, thank you, Uros. So our choice for a modular was a DDS, or direct digital synthesizer. What it is, it's an IC that takes a reference oscillator, 25 megahertz, a sine lookup table, and a 10-bit DAC and produces sinusoidal waves. Why we chose this was because, one, it had a very high resolution output on the DAC. It had a changeable frequency, which is what we needed for frequency shift keying, and thirdly, because it was very time efficient to implement. And how it works is it uses SPI, or serial peripheral interface. And what serial peripheral interface does, it has 3 lines. One, slave select. Slave select is active low. When it's low, the device knows it's being talked to. It has a standard data line with 0 and 1 binary bits. And then it has a clock, which tells the device when to read in bits. We chose the clock frequency for us to be able to change the frequency in about 1 millisecond, which allows us to achieve a 5 millisecond period on our bits. Next, we can see a example waveform where you can see 13 different bits with 5 golden bits at the start and 8 bits of data, which represents an ASCII F. You can see when it's idle, there's a waveform that's 5 kilohertz that just keeps the transmitting amplifier charged up, and you can kind of see how the frequency changes during those bits. Next, I'm going to hand it off to Brady to talk about the transmitting amplifier.
Thank you, Jeffrey. I'm going to talk about the power amplifier. Our power amplifier runs on a DC to DC converter of 24 volts and negative 24 volts. The reason we had to implement this is because we wanted a higher output voltage swing. It also does DC offset correction. This is because the DDS passes a signal that is offset by about 0.7 volts. And in order to get the most voltage output swing, we had to get rid of that DC offset. And as you can see on the graph on the screen, the green is the input with the DC offset, and the yellow is the output with the offset eliminated and the signal amplified. Next, I want to talk about the omnidirectional transducers. We noticed there was great attenuation with the omnidirectionals compared to the directional transducers. Therefore, we had to come up with another method in order to send the signals farther distances with the omnidirectionals. So we came up with this configuration. There's a master power amplifier that has most of the gain. That output voltage of the master amplifier is then put into the inverting pin of the slave amplifier that is set at unity gain, which will then give us a 180-degree phase lag, and it will allow us to double the output voltage swing, therefore giving us larger range of signal transmission. Next, I'm going to pass it off on to Manny. He's going to talk about the transducers.
Thank you, Brady. So one of the key components that came to in order to get our product to work was the transducers. It was going to be how are we going to send the signal from one end of the pole to the other. Then the way that it is done is through the transducers. Then basically a transducer is composed of a piezoelectric ceramic cylinder or disc, depending if it's omnidirectional or directional. Then when you apply an electric voltage to this ceramic cylinder or disc, it then induces an acoustic signal which can be sent through the water. Then if you're on the receiving side, it receives that acoustic signal and it induces an electric signal that came in at the same frequency. Then in order to start off, we started off our project with directional transducers off the shelf in order just to be able to prove the concept that we can send one signal from one end of the pole to the other. However, when it comes to trying to communicate with the sub that is moving around, the directional transducers were not going to be enough because they have to perfectly face each other in order for the signal to be received. Then that is when we need to implement omnidirectional transducers. Then we wanted to make omnidirectional transducers out of the following frequencies: 47 kilohertz, 98 kilohertz, 65 kilohertz, and 57 kilohertz. We also wanted to use a different range of frequencies to see which frequency best fits our application and what were the different effects on the system. Then, in order for those to be made, they needed to be potted in custom-made fixtures that guaranteed the proper amount of urethane, because if more than urethane was used than needed, then it caused the signal that was coming out to be distorted. Then, as we bring it back to how Brady was talking about the power amplifier for the omnidirectional transducers, they required a way more amplification because of the attenuation. Then when we tested the directional transducers and we sent a signal that had a peak-to-peak voltage of 30 volts, we saw that the signal received had a peak-to-peak voltage of 1 volt, giving us an attenuation of 30 volts per volt. However, when we apply that same test to the omnidirectional transducers, we got an attenuation of over 100 volts per volt. That is why they needed much more amplification. And now we'll pass it off to John, who will speak to us about the testing.
We're gonna pass it off to Nate. Talk about the big pass filter.
Yes, so basically once the signal is picked up from the pool, the next step is to filter out the noise from a waveform. And to do that, we are using the UF42 device from Texas Instrument. The two devices will compose a fourth-order bandpass filter. As you can see on the top, we having a bandpass filter for 77 kilohertz and the bottom for 50 kilohertz. The device came with 1,000 picofarads on the chip, which are trimmed to 0.5% accuracy, and in turn eliminate the need for external capacitor, giving us a real accurate frequency and also the Q point. The device will be operating on a plus minus 12 volt supply from the onboard DC to DC converter. And the reason we're choosing this device is because of its design simplicity and also of its compact size. When designing the bandpass filter, we are implementing the software from Texas Instruments. And three things to keep in mind is the center frequencies, the bandwidth, and also the type of configuration. The reason we are choosing the butterboard configuration is because we want to maintain a really good time domain response, as well as maintaining a moderately sharp cutoff frequency. Up next, we compose our bandpass filter, and here's its finished product. We are tested in the lab using function generator, power supply, and oscilloscope. Right here, you can see the voltage gain versus frequency of our bandpass filter. If you take a closer look, the 77 kilohertz on the left and the 50 kilohertz on the right are a little bit off. And the reason being is because we are using a 5% tolerance of resistor. Up next, we tested it out in the pool. The top signal that you can see in the yellow is the input signal coming from the transducer, and the bottom is the output sine wave from our bandpass filter. So we can say that it's definitely working. From here, the two signals are then passed on to the VGA for further amplification to meet a certain threshold voltage. And I'm going to pass it on to Davey to talk about his VGA.
Thank you, Nate. The variable gain amplifier will amplify the signal from the output of the bandpass filter. So depending on the level of the signals, whether the two subs are closer together or farther apart, the variable gain amplifier should be able to vary the gain and amplify the signal to a suitable level and pass the signals over to the envelope detector and the ADC for processing. To achieve this, we implement the variable gain amplifier using the TL072 from the Texas Instrument. And the circuit will be constructed using the inverting op amp. The input resistance is fixed to a certain value. The feedback resistor will be varied, and that should adjust the gain. The first version of the hardware we have the dual op amp and use the trim pot to adjust the gain. This is currently being used right now during our pool testing and the fish tank hardware system tests. The second versions will have the dual op amp IC plus the digital potentiometer, which is the MCP4231. And this is needed to control the resistance of the feedback resistor digitally using the SPI bus from the DSPIC. The variable gain, the range of the gain we can achieve out of this is 1 through 32 volts per volt. And the supply voltage will power this device is plus or minus 5. This will come from the power management board. So in the future, we wish to be able to control the variable gain amplifier using SPI bus. And with the help of software and embedded system, we would like to employ automatic gain control algorithm. Next, Mark will talk about the envelope detector.
All right, thank you, Davey. Now, an envelope detector is an electronic circuit that removes high-frequency signal from the output. The reason why we're using the precision envelope detector is because the ADC channel cannot process negative voltages. Therefore, we are sending the envelope signal to the ADC channel for sampling. And we were able to build the precision envelope detector by meeting certain requirements, specification. First, we want to make sure that both envelope detectors are working simultaneously using the TL072 dual op amp. And next, the time constant. We made sure that the time constant is at 2 milliseconds to give the ADC channel enough time to sample. And this is our final product design of our envelope detector. Next. And here's a waveform of the envelope detector working and removing the negative voltage of the bandpass. And this can easily be read by the ADC channel. And I'll be passing it to John for the hardware.
Thank you, Mark. Hi guys, I'll be talking about the hardware system test setup. We have two setups here, one in the fish tank and one in the pool. The reason why we have the fish tank is, one, it's going to be shown on senior design day, and also it's more convenient for us. Here we're going to be sending an ASCII character from one laptop, then converted by the modulator, amplified by the power amplifier, then it'll be transferred to the transducers. Next slide, please. Sorry, can you go back? There you go. Here we have two pairs, one being for our frequency shift keying, since one pair is only tuned for a certain frequency, 77K being bit 1 and 50K being bit 0. Now for the receiving side, we have the our signal will then be filtered by the bandpass filter, amplified by the VGA through the envelope detector, then sampled by the ADC channels. The ASCII signal will then be shown on the laptop. Here is Nate sending the ASCII character on the left, and now we're seeing it receive on the right side. And trust me, that's not fake. For a pool setup, we have the same exact one, transmitting and receiving. The only difference is that our transducers are farther apart now. And if you can move on to the next slide, please. Now, before we had our transducers right up against the wall, and this caused reverberations. Now, since our submarines aren't going to be directly against the wall, we decided to mimic them and move them farther out into the pool. Now, for our test results, will be told by Jeff.
Thank you, John. So what I'm going to do is I'm going to take us through all the different stages of our hardware solution and show us oscilloscope waveforms of each step. This first step is the output of the DDS, and this shows you the binary that we're sending out. This is the same as before. We're going to be sending an F through the water with our 5 golden bits at the start and our idle 5 kilohertz frequency. On the next slide, you can see the increased amplitude after going through the transmitting amplifier, and now it's also centered around 0 volts. On the next slide, we can see the input of the receiving transducer, and this is the output waveform that we get. You can see that we're still getting the same binary on the 2 different 77 kilohertz and 50 kilohertz rails. On the next slide, we can see the cleaned up version on the output of the bandpass filter, and we can still see the same binary on the screen. And then after this, it goes through the variable gain amplifier, where we have the voltages set at the same voltage and above the threshold that the ADC is expecting on the microcontroller. And then on the next slide, we can see the output of the envelope detector, which gives us a waveform that can be sampled by the ADC of the microcontroller. Next, I'm going to pass it off to Lee to talk about our benchmarks.
Thank you, Jeff. So the standard of our project, we compared 2 underwater acoustic modem made by Wu International University and UCSD. It was important to maintain a low power consumption of around 4.5 watts and be able to transmit signals up to 7 meters. Our underwater acoustic modem needed to manage transmitting 200 feet per second. So to upgrade for our measured benchmarks, we achieved an efficient low power consumption of 2.5 watts, and also transmitted 200 feet per second. On the other hand, due to the pool constraint, we couldn't transmit a distance of 70 meters, but we did 25 meters. To meet all these benchmarks, cost has to be taken into consideration. And to talk more about that, I'm going to pass it on to Sabat.
Thank you, Lee. And just as we were able to meet the majority of our benchmarks, we were also able to meet our budget of $1,500. We were able to go roughly under our budget, around by $300. And in addition to that, we also, for your visibility, included a cost of the estimated cost of our entire product. However, this takes away some of labor fees, obviously, so that's for that. And for our milestones, additionally, we were able to meet the majority of our milestones that we established on ourselves in the beginning of the semester. However, we had one delinquency, and that regarded the testing of our omnidirectional transducers. We were able to test them in the fish tank. However, due to our inexperience with dealing with omnidirectional transducers and supply-related issues getting parts in on time for testing on time, we weren't able to complete that. However, we were able to fully integrate the system testing based on the directional transducers. And so to summarize, earlier Jeffrey noted that, or made a point that underwater communication isn't new, as it's been used very extensively on underwater applications that were extremely low depths and extremely long distances. And for our purposes, we had to scale this down into shallow depths and short distances, which is a really new niche of underwater communication. So with that said, when we got this project assigned to us, initially we were skeptical as whether or not we would be able to produce a product that would be not only reliable, but be robust. However, due to the combined efforts of our team and our guidance from John Kennedy and Mechatronics, we were able to make a really reliable product, and we are satisfied with our results. So thank you, and are there any questions?